All right. Good evening, everyone, and welcome to the second edition of PerfUp. This session focuses on the role of artificial intelligence in performance engineering. PerfUp is powered by Cisco Labs, and today we have two speakers, each taking on a different aspect of artificial intelligence in performance engineering. Before we get into today's session, I'd like to give you a quick introduction as to what PerfUp is about. PerfUp is an initiative to bringing together the best minds in the software engineering arena to share knowledge on new trends and discuss best practices in the field. Each PerfUp event will feature a panel of experts who speak on their knowledge and experience in the area to individuals to tackle performance engineering. Let me introduce your speakers for the night. First up, we have Asanka Vitanage. Asanka is an associate architect for quality engineering at Cisco Labs. He has over 12 years of experience in the quality engineering and QA automation, performance engineering, continuous testing, etc. He is passionate about implementing automated test frameworks and adopting DevOps practices to improve testing speed and productivity. And as a part of Cisco's enterprise performance engineering team, he is currently focusing on R&D related activities, again relevant to performance engineering and application resilience. Next up, we have Malit Jayasinghe. And Malit is the Vice President of Research and Artificial Intelligence at WSO2. He is a computer scientist, author, blogger, and software architect with more than 15 years of industry experience in designing, developing, optimizing complex software systems. Malit also is a co-author of the book Performance of Web Series, and in his current role, he is providing leadership to multiple product teams, working in the areas of artificial intelligence, machine learning, observability, performance, and finally research. So, Malit, I think we can start. Over to you.
Thanks a lot, Prabha. It was a very nice introduction. So today we have a very interesting topic to talk about, which is how we can use AI to solve problems in the performance domain. Right? So before getting into the main topic, I would like to give a very sort of a brief introduction to performance. Now, performance, as you know, it plays a very important role, and it is one of the most important non-functional requirements. Right? And also we have seen, so basically when certain customers do vendor evaluations, they even go to the extent of, evaluating the performance of different products, right? So based on these results, they make that final decision. So it can be a major selling point, right? So if your product is performing, if it has very good performance, that's a very good thing. So also the performance is an exciting and challenging discipline. Also, it is complex. So those who work in the performance area, I think they know it is complex. It's complex because these interactions between different systems is quite complex, and it's very difficult to sort of reason and understand these behaviors. They are in fact related in, I would say, unexpected ways, right? Also, another characteristic of performance is, at least to a certain extent, performance is subjective. Right? I mean, usually the technology disciplines are objective, right? But performance, sometimes it depends on, who looks at it and, how you look at it, right? What is good and what is bad can be quite subjective. Right? Next slide, please. Okay, so I want to give a very brief introduction to these two performance metrics, because I will be mainly sort of, talking about these two performance metrics throughout this presentation. Now, as you know, throughput is one of the main performance metrics that we use to evaluate the performance. Now, if I am to just explain the behavior of throughput, with the increasing load, or the number of users or the concurrency, the throughput increases linearly with the load up to some point, and then it sort of stagnates, stays constant, and then it starts to degrade. So that this is the sort of the behavior of the throughput. So the next metric is the latency. Can we go to the next slide? Okay, so the latency is, it's not a single value, right? So if you do a performance test using JMeter, you get a lot of latencies. So we call the latency actually exists in a form of a distribution, right? So these individual latency values makes up a distribution. Now these distributions can be of different forms. So I have drawn this distribution on the left for a particular use case. Now from this distribution, you can derive certain statistics. So it could be the average latency or the 90th percentile, 99th percentile, and you can even go to the extent of basically 99.9 percentile, right? Next slide, please. So if I take the average latency, so the way in which the average latency varies with the load is, it increases linearly and then up to some level, and then it sort of increase a bit faster at a higher rate. Then it increases exponentially, right? So that is when you call the system has gone out of steady state, right? Okay, so this is a very brief introduction to these two performance metrics. That now we can sort of move to the main topic of today's discussion. Can we go to the next slide, please? Thank you. Okay, so if you take a look at performance, there are different areas in performance where people have tried to use AI. Right, so I have sort of highlighted some of these areas. Now, these are actually very big areas, right? So under each of these areas, there are multiple different use cases, right? Now, so let's go through each of these, areas in a little bit more detail. So the one area is performance optimization, right? How can we use AI to optimize the performance of a product or a system or a microservice application and so on. So that's one area where you can use AI. Then related to this is the deployment optimization. They are sort of related, but you sort of try to optimize the deployment level stuff. Like for example, if you're writing a microservice application, now you are going to deploy, how can you compute the core sizes? Like how many cores that you should allocate? Or how can you, design a more efficient scaling algorithm, right? Then another big area, now this is quite hot these days, basically using AI to detect performance-related bugs. Another term for this is anomaly detection, right? So people are working on this. So we are actually also working on this one quite extensively. And then, so this is detecting bugs, right, in your application. Performance-related bug can be a CPU spike or whatever. We'll get to the details later. Then you have troubleshooting. Once the bug is detected, you want to know, you want to get to the root cause. And can we use AI for that? That's another, category of performance-related problems are there. Then, of course, you have the testing, performance testing, and basically the problems in performance testing area, developing tools, and so on. The last one is basically the performance prediction, forecasting, and modeling. This is also another area that people are working on. So I will. Let's now take a look at some of these areas in a bit more detail. Can we go to the next slide, please? Right. So yes. So the performance optimization. Let's go to the next slide. Right. So one way to optimize the performance is by tuning. Right. So this is not the only way. Actually, tuning comes later. So first you have to write it and then develop your app and then test it. First, basically, you try to optimize your code, right? Because the highest improvement in the performance, you can't get it by tuning. You'll have to actually optimize your code, like use caching, whatever those techniques that optimize, use of better algorithms, data structures, etc. But the main use case which I'm going to look at is the tuning. Tuning also can result in significant performance improvements in certain cases. So the basic idea of tuning is there's some system, right? And there are parameters. So another term for this is knobs. Now, the performance of this system or the product or the microservice depends on these parameters. So the objective is to find the optimal parameters such that you get the best performance. So the performance metric can be throughput or latency. You actually try to optimize one of these, and also there's a possibility of trying to optimize two at the same time, but it's a kind of a little bit more complex use case. Next slide, please. So what are the parameters we are talking about? Like if you're building kind of some application where you have to deal with buffer sizes, connection pools, and thread pools, these ones actually have a significant impact on the performance, right? So these can be tuned and the performance can be optimized. Or database parameters. So people have made attempts to use AI to optimize these parameters. Databases have certain parameters. And if you're writing code in Java, JVM has parameters, right? So these are the things that we actually can optimize. There are, of course, many other scenarios also. Next slide, please. So the basic architecture, I mean, there can be multiple apps or set of apps. Set of apps in the sense it can be microservices application. So the basic, the algorithm is that you have to start somewhere, right? So you start with some default values and you run a performance test, right? So once you run a test, you get performance results, right? The throughput or latency. So then what you do is you feed this latency or the throughput, whichever the metric that you want to optimize, or could be the 99th percentile or whichever. You feed it to a model together with the parameters that you have used, plus certain features. So features here are the things such as CPU utilization, the memory utilization, and so on, right? Then the model will decide the next set of parameters to run the test, right? Next set of parameters to run the test. So then basically, okay, slides are gone. Then you run the test using the new set of parameters. Then you again get another performance value. Then you feed it back to the model. So this process continues. It's like an iterative kind of an algorithm. Eventually, it is supposed to converge to some value, some set of values, so that those are the optimal parameters under which you can get the best performance. Next slide, please. You can skip this. Yeah, next slide. Yeah, so the tuning can be of two forms. You can do such tuning in an online setting, that is while the application is running in production. I'll show you one example. Or in certain cases, you can't tune these ones online, right? I think if you take the JVM, for example, you can't change a JVM parameter like in production. You have to restart, right? So both of these cases are possible. Next slide, please. So in terms of approaches, now we have actually used quite extensively the Bayesian optimization with the Gaussian process, which is one of the machine learning algorithms which can be used for these sort of optimizations. And then the other popular one is the reinforcement learning. It maps to that sort of algorithm, the high-level idea which I described to you earlier. Then also there's a possibility of using any other sort of algorithm, especially if you are doing this tuning offline, right? You have a data set, you know the performance, and then you train a model. From that model, you can basically get the best performance for a particular sort of scenario. Next slide, please. Right. So here in this case, so this is a case where we have tried to tune the thread pool size or the worker pool size of a microservice. Okay. So just thread pool, just one parameter we are tuning. So you probably know like the thread pool size in this sort of, so these are the threads that are handling the incoming requests, right? You serve it and then you send the response back. So there is this theory which says the optimal thread pool size is equal to number of cores. But that is only the case if your system is completely non-blocking. Like if you have designed something which is completely non-blocking, then you may not have to tune these pools. You can just set it to number of cores. But in reality, it's very difficult to design completely non-blocking systems due to various reasons. Like if you take, for example, a database call, when you make a database call, basically that thread gets blocked, right? Okay, now we have a way to deal with those cases, like you can do it in a non-blocking way also. And also like the other case is like, you might be developing an app and the underlying libraries may have certain level of contentions or synchronization methods which you don't have control over, right? So in such cases, basically, that theory doesn't actually apply. So therefore, you need to use more threads than the number of cores. I hope that is clear. So, but if you go to the other extreme, where if you put like say thousands of threads, then you have the issue of context switch overhead, right? The context switch starts happening, and then again the performance sort of degrades. So here, what we have tried to do is to see whether we can get better performance compared to the default. Now here you can see like the default is the blue line. So this is the 99 latency percentile. So the lower the value, the better, right? Because these are the latency percentiles. And then we are here using one of the techniques. This is the Bayesian optimization. You could see that this is happening online, right? It basically there's a little bit of an exploration, so the latency degrades a bit, and then but that comes down. So in this case, it's a 46% improvement. Also, I have the throughput. It has not really affected the throughput, but there could be cases where it may have an impact. Next slide, please. So then again, there's another use case where we are trying to tune two microservices. Right? You tune the thread pool sizes of two microservices to optimize the performance. So the first one talks to the second one sends a request back to the first one, and then it goes back to the client. So in this case, the improvement is higher. Next slide, please. Next slide, please. Yeah, thank you. And so here, this is done by actually one of the students. So here, actually, she has tried to tune the database parameters. So this is for an IAM workload. Here also, you can see the kind of improvements that you can get. So another technique which is used here is this genetic optimization. So any kind of optimizations can be used to solve these sort of problems. Next slide, please. Okay, let's now take a look at the deployment optimization also very briefly. Next slide, please. Okay, here the problem, I'm going to narrow it down, this problem. So here, let's assume that there is a microservices application, and you want to compute the number of cores for each of these microservices. And and then let's also assume that the number of cores are fixed. Like say, for example, you have fixed budget, right? Next slide, please. So this is the application that we are talking about. There is microservice 1, microservice 2. So we want to find what X and Y are, right? Next slide, please. Okay, so in this case, you can see like, so this basically, this shows the performance numbers under different core sizes. So if you take the first line, for example, the microservice 1, we allocate 1 core, and for the second one, 3 cores. So in that case, there is the throughput is 1730, right? But if you take a look at the line that is highlighted in yellow, you would notice that you are getting 5067 TPS. That's a significant improvement compared to the first line, right? So, but the total number of cores is fixed. So 2.5 plus 1.5. So this problem actually, it maps to the same problem that I have explained earlier. You have to run like tests multiple times. And in each test, you have to sort of change the cores. The core size will be basically decided by the algorithm. And then it will eventually converge to a value, right? So that is one use case in deployment optimization. Let's now move on to the next slide. Okay, so this is actually a very hot topic these days. Now, compared to the previous two, a lot of people are actually working on this. Companies like AppDynamics, Dynatrace, there was another one, New Relic. So this is about detecting, anomalies, performance anomalies in running applications. Next slide, please. So anomaly is actually anything that is not normal, right? Your application is not performing as expected. So the anomaly detection is basically pinpointing where that issue is, right? Next slide, please. So you have to ask the question, why do we have to do this? Of course, we cannot afford to sort of analyze all of these data, right? It's not possible, right? When you have a lot of applications running, you have to have an automatic way of detecting these behaviors and patterns that are not normal. So that is the main reason for doing this. And then basically the users of that apps should be informed, right? So one thing that you need to consider is like if it's in a cloud environment where the developers come and develop apps and then deploy. Do we need to sort of have different models, or can we do this using single model for all type of applications? Because the workload characteristics are different, right? So if you go for if you are to do multiple models, model per app, then that can be quite expensive as well. So these are the things that we have to consider when developing such algorithms. Next slide, please. So what can cause these sort of anomalies? I mean, there can be multiple reasons, right? So there might be CPU hogs, or there's some bug in your code, or memory related issues, user surges. You can get like a spike, load spike, or slow backends. That is also another reason for these sort of anomalies to occur, or the network saturations can be another reason. Next slide, please. Now, so the anomaly detection, as I mentioned earlier, it's a very broad topic. Now, one way to do the anomaly detection is basically using application metrics and system metrics. So what do I mean by application metrics? So this is basically the response time, the throughput, the percentiles, and so on. System metrics are the things like CPU utilization, memory usage, and so on. You can even, get certain kernel level stats such as context switches and all that also. Next slide, please. So at a very high level, there are two ways to do this. So the first one is called the univariate one. So the univariate anomaly detection, you look at the individual series. You look at the, say for example, you look at the latency and you try to see certain, patterns. For example, spikes or trends, like latency is increasing, or level shifts, latency goes down. So these could be anomalies, right? So that is one way to do it. Another way to do it is, this is called the multivariate. So in that case, the model will look at multiple of these metrics together, right? You don't look at it as individual metrics, rather you look at everything together. So for example, here I have a case where there's a network saturation. So this is actually coming from a real sort of a scenario. So the network is saturated, and what has happened is you can see that the average response time has gone up. Makes sense, right? And the CPU utilization has gone down because there's no work to do, right? I think there's a slight drop in the load average. So basically, so this is called the multivariate. So the model will decide whether there's an anomaly or not by looking at multiple metrics, right? Next slide, please. So this is a screenshot of one of the products which we are releasing very soon. So this is actually called the Choreo platform. So what happens? So this is actually detected using this multivariate anomaly detector. What happens is it detects these abnormal or not normal patterns and then alert the user. So the user will get an email. So that email will have a link. So I'm getting a link. Hello. That email will have a link. When you click on that link, it will take you to this, we call this the observability view. It will pinpoint where this anomaly is happening and the time, and also you can correlate the logs to this. So as you can see in this particular case, the number of errors have sort of increased. The throughput for some reason has increased. Maybe it's because of the errors have gone up. Latency has also increased. There's a CPU level shift and so on. Right. Next slide, please. Yeah. Okay. So what are the techniques? Actually, for this problem, people have actually used various different techniques. You can even start with simple, statistical sort of things such as ARIMA and so on, or the other technique that is used for simple anomaly detection is this the Gaussian distribution. And if you do have the label data, so we have actually tried this but didn't quite work. Label data means you know that these are the anomaly points. Right? So we have a data set and you know, okay, these are the anomaly points. Then you can sort of, train the model and then tell the model like, okay, basically these are the anomaly points, and when similar ones occur, then detect it, right? And then also the unsupervised method. There's no label data. You just train it using a lot of data, which you consider as normal data. Anything that deviates from that normal data is detected as anomalies, right? So recently there is some work that is published which actually can do this multivariate anomaly detection very well, right? So I think there's significant improvement in the accuracy from the previous implementation. So one of them is the DevNet, and there's also a few other approaches that have been published. So if you are interested in those, I can provide the references to those papers also. Next slide, please. Okay, so the last the area that I am going to discuss is performance forecasting. Right. So even like I said before, even under performance forecasting, there are many use cases, but I am going to be basically focusing on one main use case here, which is providing development time performance feedback. So this is something which we have done and we have this working right now. So let me now explain some details. Can we go to the next slide? Thank you. So we are actually trying to basically estimate the performance of a integration program. So this is a category of programs that have a lot of external calls, right? So these are called integration programs. So the main use case is that the users will come and develop one of these programs in the cloud. As he develops, we want to show what the performance might be. Okay, so this is the development time user experience. You don't need to run it. That's the main thing we are trying to achieve. So now, usually in these sort of programs, the main factor that determines the performance is it is actually the cost of doing the API call. There's very little happen in the service itself. Right? You have to make a call to some external endpoint. It can be Salesforce or send an SMS notification, or it might be just another service that you want to call. Right? Next slide, please. Okay, so to give you a little bit more sort of idea. So here, so this use case, it's basically what we want to do is provide COVID-19 cases per million people in a specific country, right? Now, so this, just think of this as a service, right? So this service will receive the country code or whatever that code, and then the response should be COVID-19 cases per million people in that country, right? So it receives this request and then it has to sort of calculate this. So it actually does two API calls. So I have highlighted those in red, right? So the first one is actually creating that object or the client object. The second line is, line 12 is the creation of that client object. Line 13 is the actual code, right? So you basically talk to that endpoint and get the COVID-19 cases in that particular country. So you pass the short country name code, right, which comes in the request. So then you have to get the population. So now you know the number of COVID-19 cases. So then you call this World Bank API and then get the population. Then you divide the total cases by the population and then send the response back, right? So hope this use case is clear. So then, okay, can we go to the next slide? Okay, what we want to, so this of course will be receiving requests in parallel, right? So basically this is a service that is deployed in production. Now you're running it. So it will be getting concurrent requests. What you want to basically get is the two curves. So these things I have sort of described earlier, which is the throughput and the latency curve, right? With the concurrent users. So that is the objective. Next slide, please. So this is important because of number of reasons. Like if you have this kind of sort of a plot or a graph, then you can understand whether you are meeting the SLA. So even you can detect certain bugs, like if you put it inside a while loop, you will immediately, or a for loop, accidentally, you would immediately see the latency going up and throughput going down, right? Also, certain endpoints might be like too slow, right? In such cases, you will immediately notice it, and you might be able to find an alternative service that you can call. So there are like multiple reasons why one wants to sort of have a feature like this. Next slide, please. So how do we do it? At a very high level, okay, not going to go into the detail. So there's this area of mathematics called queuing theory and or queuing networks. We map this one into a queuing network. So each component, including the low workload generator, the guy that sits in the middle, which is the microservice which receives the request, and then the external APIs, we represent this using a queuing network, and then we derive the final performance using this. Next slide, please. So what we do is the first step is to model these interactions. So we collect the data for each of these individual action calls, and then we build a model for these individual ones, right? So the first one is, for example, the first interaction and the second one, right? So, but to do this, so initially there won't be any estimates, of course, right? When they first come, right? But as you get data, basically you have to collect them and then store them, and then you have to periodically train these models, right? And then when you come and develop the use case, if that use case has the same, connector, we call this the action call. So, for example, connector might be SMTP connector, and action call might be, send email or whatever, right? So, if there's a model, then we can basically compute the overall throughput for the entire service. Next slide, please. Yeah, so this is the data collection pipeline, right? So you collect the data for these interactions, you store it somewhere. It can be a database, or if it's Azure, it can be ADX or whatever, and then you periodically train, and then you store these models, right? And then we use those models to provide the estimates. So can we go to the next slide? Okay, so let me see if I can very quickly show you how this works. Share the screen. Are you able to see the screen?
Yes, Malit.
Yeah, so, okay, so here we have this, this again, the use case is slightly different. It's not the COVID-19 one, this is something else, but it doesn't matter, right? Okay, so we have a use case. So this is the low-code diagram of that use case. Now you can see so basically the forecasted performance is shown here, right? It says concurrency 1 to 5, this is the latency range, and then it gives you the TPS range also. If I click on show more, then basically I get these curves, right? So this is the curves that I was talking about, basically how the throughput and latency behave with the number of concurrent users, right? So you can click on it, and basically for each point, you can get the value. Also, you can, in fact, even go to the code. Let's close this. So even in the code, we have added these code lenses sort of a thing, where you can basically see these numbers coming up. So in this case, like this is the external call, right? So if you have multiple of these, then of course if the data is there, if there's a model, then you would see the forecasted performance for each of these connector calls, and then also the total performance, right? So this is how it works. Now let me stop sharing. Okay. Can we put the last slide? Okay, so let me now try to conclude. Okay, so today's discussion or in the presentation, we basically looked at how we can use AI to solve various problems in performance, right? Now, as I mentioned earlier, of course, performance is a very interesting discipline, right? Exciting. I think when you combine these two things together, it becomes even more interesting, as you may have seen, right? So different companies and different research groups are working on these different problems, right? So, but they may not be interested in the other use cases. For example, the observability is completely one area, like the bug detection. So one good thing is that now earlier there is, at least to some extent, this AI stuff actually didn't get into production, right? Because there's a gap between what the guys in the research are doing and what is actually getting used in the industry. But I can see now it is now changing, right? So people even go to the extent of changing the auto-scaling algorithm. Basically, go and change the auto-scaling algorithm and then put an AI-based auto-scaling algorithm. So people are actually now adapting these things because the main reason is it is actually solving a real problem. You have to solve a real problem for it to become useful, right? So AI is not just a marketing. I mean, some people may think it that way, but you'll have to solve a real problem for it to become useful. So, so I think that would bring us to the end of the talk. And so thank you very much for listening, and over to you, Papa.
Okay, nice. Good evening, guys. And thank you for the interesting session, Malik. So I think we had a lot of things to get from that. So within the today's session, what I am trying to discuss is how AI and machine learning can be utilized in the context of performance engineering, and also especially in the area like how we can utilize them on the load generator optimization and load generator improvements. With that, obviously, I am kind of suggesting something like we have some gaps with the existing default tools. We have to take some steps to improve it. So to start the session, let me give a bit of context by myself. So I am working for Cisco's enterprise performance engineering team, and so as a team, we are responsible for doing a lot of R&D works related to the performance engineering and tooling stacks and building platforms for other teams, other QA guys to use. So with that experience, so I'm kind of I have identified few challenges we facing with the enterprise testing context, where the tools are we need to improve to fill those gaps. So if you get a Fortune 500 company like Cisco, right? So we do billion plus worth of transaction, business transaction annually. So that means like there will be very efficient application stack, software stack should be there to support that kind of a business uh, to achieve that kind of annual revenues, right? So to support that kind of a thing, and in the enterprise, we have very complex distributed enterprise software stack. So it can be very modern, cloud-driven, microservice-driven applications, but it can become like very monolith AS400 mainframe kind of a very legacy tech as well. So in the worst case, this can be like mix up all together, right? So whatever the performance testing tool we are using won't be able to cater or work with all these application stack as well. So in that case, we may have to bring on different tools to load test different areas of this application stack as well. Also, in this kind of a enterprise setup, there will be many application development teams, many engineers, many QA engineers. They also kind of continuously develop, and they want to do a performance testing continuously for their releases and so on, right? So managing a performance testing environment is a real cost. So people who have done it know it, right? Now it's actually become much easy with this cloud adoption, virtualization, containerization, and so on. But when we started the career, actually, we started with the physical machine. It was very tedious because we have few machines, we want to generate the load. If the machine is not enough, we want to bring on the new machine and set it up, run. So that's kind of a repetitive task. So we had those kind of challenges. So now we have like more of a cloud-driven, easily scalable solutions. So I will be discussing how we can utilize those modern DevOps tool stack we can use, and also how AI and machine learning can play a role on this scalability, automation, and also the monitoring those areas. So as Malit mentioned that if we want to kind of come up with a machine learning model, we need a lot of data, right? So the problem here, I think, I see is that there is no enough data to actually come up with proper models so that we can do auto scaling and also like performance stat analysis kind of a things in more meaningful way with the AI driven technologies. Babak, shall we move on to the next slide? Okay, so let me in detail explain what kind of a test expectations we have from the enterprise perspective on a test environment or the performance execution platform management, right? So as I mentioned, like we have so many teams, right, within the organization. So it's not affordable or it's not feasible to manage dedicated environments for these each setup, each teams. We need some centralized solution, right, where people can come in and in a self-hosted manner, in the self, they come and then self-service with their scripts and kind of execute the test. So if we can kind of set it up that kind of environment within the organization, then it will speed up the performance testing practice on the organization. So as I mentioned, like as an enterprise context, like we have to generate a lot of loads. So to generate the lot of loads, we need that load server capabilities. Our load generator should be able to scale and generate that load, and also our environment should be lean and agile. Otherwise, it will be a lot of cost for the organization. And since there are several teams want to run the test, our platform should be support the parallel execution, and also should be cloud and containerized driven so that we can scale and we can be more agile and lean, right? So then other things like continuous performance testing, supporting the continuous performance testing. So for that, our platform should support inspect as code, performance as a code, test as code kind of approaches, so that people can manage their testings as a code, and also kind of they can version control those things. So there are that kind of manageability and maintenance, and also we know we have the track of what's going on everywhere. So overall, with this all those features, we should have the lower maintenance cost, so the business is not affected, and we are not adding a burden to the organization. So these are the mainly the expectation from this environment perspective. So in a simplified way, like we need more scalable environment, right? So what we should try to achieve is like come up with the platform where we have this scalability, so the teams can come in and onboard and execute their test easily. So they don't really need to worry about the infrastructure level things or the configuration level things. Next slide, please. Okay, so let me explain the current situation, right? So I guess everybody is familiar with the JMeter. So if we get, this is the way actually we normally start and where we actually run the test in most of the cases, right? So we prepare the JMeter script, we set up one JMeter installed machine, right? From there we try to generate the load, right? So but the problem here is like if the load we need to generate is very large, then there's a high possibility that we will be getting out of memory issues on the JMeter on middle of the test, right? So it's more of bomb to burst in the middle of the test, right? So in such a situation, we have to repeat our test, right? Repeating the test, like repeating the same work again, and maybe improving the memory allocated to the JMeter JVM, we can retry it again, but and again it can may fail. So for that, JMeter has one solution. Next slide, please. So that is actually distributed distributed JMeter setup. So here they provide like to support to bring the multiple machines, so and generate the load. So, but the problem here is that setting up this is kind of a very tedious. We need to bring on the physical machines, install the JMeter, configure everything, and so on. So once we set it up, we can run for one test. But if the another test need more machines, then we have to set it up again and again, right? And also we can only run one test at a given time in this kind of a setup. So because of these reasons, we have in the enterprise context, we can't just manage this kind of a distributor setup and do this everything. So we need something more lean and something more agile where we can set it up. So let's move on. Okay, so let's see like what's available in the market. So one thing is place meter. So I think some people may already have used place meter before. Like there are a lot of, if we search for JMeter, there are a lot of place meter content coming in, right? So place meter is something JMeter as a wrapper, right? So it's kind of a cloud solution where they provide load generators. We can bring in the JMeter script and run it. But in the enterprise perspective, because of the security concern and also because of the cost and also because of those kind of reasons, like going with the base meter is not practical, especially like in the enterprise kind of a situation. Like as I said, we may have to take like different approaches to test the different application. Like in some cases we can use JMeter. In some cases we want some automation, like bring in the automations together with the JMeter API and execute something like that. Like we need like different solution, but that kind of a customization is not available with the base meter. So other solution is like cases. Cases also JMeter like performance testing tool. Cases has something called Kubernetes operator. So where it's actually creating this cases clusters on the Kubernetes. So basically we can provide how many load we need, load generator machines we need, and those configuration, then that operator will create the cluster on the Kubernetes side. So here problem is like K6 only provide a set of protocol support, like but in the enterprise context we need support for several protocols. Like we may need to test databases, we may need to load test like Kafka servers or message brokers, those kind of we need support for so many protocols. But the cases has support for only few protocols, so then it can maybe a restriction in that case, right? So saying that, but JMeter, if we can kind of come up with the solution to auto scale the JMeter and use it, then it will be a good solution. So here we have like now with the cloud adaptations and also the development practices, like we have Inspire as code, a lot of Inspire code set solution, right? So we have the capability that kind of come up with this kind of automated workflows. So here shall we move on to next? Yeah, you can go the full cycle, Baba. Yeah, let me explain here, right? So now what I was talking about, like we have to create the infrastructure automatically here, right? We can, I think any organization has Jenkins mostly, right? So some sort of CI, right? So we can prepare a Jenkins pipeline, right? So pipeline and that part of pipeline, we can have the JMeter cluster creation deployment, like we can create the infrastructure, those things, and then we can run the test, and then we can pass the JMeter results, and then we can maybe publish them to the dashboards in the real time. Those things we can do. So here we basically manage everything, like this more of a high level workflow, what I'm suggesting we can take on. So here basically a QA engineer can come and commit their requirements, like how many JMeter machines they need, how many resource allocation they need to be done on those machines, right? So those details they can come in and commit on their own GitHub repo, and pass that to a Jenkins pipeline. And as a part of the pipeline, it will create the JMeter cluster as per the instruction given by the QA engineer. Then after that, after the test completion, it will again delete that environment. So it's in that way, like we are not running the servers continuously. So we can do this on the easily on the Kubernetes, like using the Docker containers and so on. We can do it easily. So here I have shown the Kubernetes, and on top of the Kubernetes, we are doing this deployment. So other interesting aspects, like we can collect real-time statistics, right? It can be the performance test statistics. It can be the JMeter machine resource utilization or JMeter logs details. Those kind of details will be really valuable when we want to actually adapt the machine learning, because when I starting, I raised the concern that we don't have the enough data to actually set it up and create the machine learning models and train the models, right? So in this solution, we are collecting so many data, right? Just assume that we are putting this to an enterprise application. So there will be like 1,000 number of build executions or the tests going on in this kind of a setup. So with that, we will be gathering so many data. So many data with respect to the performance statistics, with respect to the server resource utilizations, and also the JMeter level logs and so on. Those insights also we will be gathering. So with that, we will be collecting set of data, and also we will be achieving auto scaling, what we like is scalable cluster creation as well. Let's move on, Prabha. Yeah, likewise, we will be, can we go back to the previous slides? Okay. So that's about the scalable setup. And then other main enterprise expectation is actually visualization and monitoring, right? So when we do the performance test, it's really important to have a real-time monitoring, because just assume that we are doing an endurance test for like 2-day endurance test, right? So in a standard manner, right, if we run this with the JMeter deploy things, right? So what we get the result only after the full test complete, like only after 2 days, right? So if there is something wrong, like let's assume that we haven't achieved the expect throughput because of our script configuration issue, then we may have to repeat it again, right? So we make that decision after 2 days. So that's a lot of cost and a lot of pre-work as well, right? So because of that, we need to real-time monitoring support and also better visualization, so that the management, everybody can have a clear idea about what's going on the test, right? So then we need to persist test results for future reference. So with this, we can kind of iteratively compare how our applications perform over the releases. So other point is like single data visualization portal, so that we have the guide, we have the test governance side as well covered from with this, right? We have all the visualization in the central place. Everybody know like what's going on, and everybody knows like where to look in case of they need to debug something, right? So other aspect is like observability, right? So in the observability concept, like we have in the observability, the main three pillars is like logs, matrices, and the traces. except the traces, we are collecting the logs and matrices in the my previous architecture I showed, like the workflow I showed, right? So with that, we will be able to support the observability as well. Let's move on, Baba. Okay, so that's what the enterprise expectation. But with the JMeter default versions, what we get is this kind of a dashboards, right? It's not actually recommended to run JMeter with the GUI mode. If we run on the GUI mode, we will get the charts on the shown on the left side of the presentation. And after the test, maybe we can generate HTML that like JMeter dashboards, is HTML report. But the problem is like it's not that very user friendly. Like if you want to query something, if you want to kind of drill down to a time a specific time, that's not possible. There are that kind of a gaps on this approach. So let's move on. Okay, so with this, right? So I was talking about ability to query and kind of drill down to a specific timelines and those things, right? So those things we can achieve with this kind of approach. Where JMeet has some plugins called backend listener. With that, we can publish data to a in plus DB kind of a time series databases, or maybe we can publish it to Elasticsearch, or maybe we can publish to a Datadog kind of application performance tool. So the JMeter has that kind of solutions. Then we have to bring up Grafana and visualize this data we store to a time series database. So with this, we will be having full control over whatever the data we gather. And also we have some central dashboard, right? So from application to application, we can switch on and view the results. So with this also, we will be collecting a lot of data on the required for the and can be utilized for the machine learning activity. Next slide, please. Okay, so other point here is now when we decide in like auto scalability kind of a things, right? If we want to automatically decide like automated like AI driven or the machine learning driven automated application scalability, then we should have details on at which level we need to scale and how and those kind of resource level details we need, right? So with this Prometheus, Grafana kind of using those tools, open source tools, we can gather those details, right? I'm referring to my architecture I have shown before, right? So with that kind of a setup, we can use this Prometheus, Grafana kind of open source tools and gather those statistics and use them on those kind of use cases. Move on. This move on. Yeah. The other point is like collecting logs. So the QA engineers can get the idea about what's going on their slave machines, and these logs also can be utilized used to build the machine learning capabilities. Next slide, please. Okay, so in this point, right? So I was discussing from the enterprise perspective, we need more scalable load generators. So with this DevOps practices, we have implemented, like I have explained, like cases Kubernetes operate a bit, and also some workflow like we have implemented like a more of a CI/CD driven approach, right? So even with that, right, what we have is like more of a idea, like before we actually in that setup, what happens like before we start the test, we should have idea how much memory CPU we need on the JMeter machine, how many JMeter slave machines we require. Those details should have at the time of test starting, right? So even in my day-to-day life with our platform, QA engineers come in and ask that question from me. So unfortunately, I don't have a clear idea, like clear say about like go with 3 machines, go with 4 machines. I can't say it because it's changed from scenario to scenario. So it's totally experience based, and I give some suggestions. So for this actually I have seen some people try to come up with equations as like equation-based models where you provide some metrics like you need like you provide like throughput details and load details, and you get some idea about how many JMeter machines you need, or how many load runner machines you need, those kind of things there. But that's more of an equation. That's not something improving, and it's not, we can't say it's like 100% accurate as well. So because of this, actually, we can't 100% get a guarantee that whatever the resource allocation we allocate at the time of we start the test enough to continuation of the test. Because in the middle of the test, there will be JMeter will be have a memory spike, and it will be crashed, right? So in such a situation, there will be a lot of repetitive works, right? So to find the best optimal capacity for the load generator machines and so on. So that's how to be do a lot of cycles and get the idea. But that will be a costly approach, right? So, but here, if the machine learning can help in, right? So since the model I suggested before, right, we will be collecting all resource allocation details, like resource utilization details based on the time, right? With the Prometheus and those matrices, we have the data. Then we can we have so many like execution details, like with the platform, with the test run on the platform, we have those details. So with that, we can come up with more of a forecasting model, where machine learning model, where we can provide our expectation. I mean, we need to generate this much of load, and then the forecasting model should be able to say that go with this kind of a configuration. So that's one of the area where I think AI and the machine learning can help to easy the QA engineers or the performance engineers job. So the other point is like the real-time scaling, right? Even though we have the forecasting, it will be it will be a forecast, right? So the model will be continuously learn, and it will improve the accuracy, but it still is the forecast. But if we have a observability driven real-time scaling approach on the application level, like for example, if we can configure, like if the CPU utilization or the memory utilization go beyond 80% mark, scale the load generators. So if we see that on the application level, a lot of people have implemented, right? So application level, there are that capabilities, like it's depend on the how you develop the application, but there are that feasibilities. So this is actually one aspect where tools need to think of, but because we have tried to look into this aspect, but with the JMeter distributed architecture right now, we have some limitations, because we have to start all the slave machine before we start the master machine, and we can't bring on the new machine in middle of the test. So there are that kind of architectural limitation on JMeter level, but at least new performance testing tool, I think we should be able to customize the JMeter to support that kind of a feature. So other point is like resource the finding the analyzing the result side, right? Finding the correlation and patterns in the testing results, right? So right now what we do is like more of a manual level. We use statistical models to analyze our performance system. Like we get like average 90th percentile, 99th percentile, those kind of statistical models to evaluate our performance systems. We can do it for like few matrices, but just assume that we are testing for like a very distributed enterprise application, where we have run several we have run the load test for several applications in parallel, and do that testing. So there will be so many matrices to evaluate, right? So it won't be practical to find the correlations and patterns in that kind of a model. So if the machine learning can be help, yeah, it's definitely can help in, right? So if we have the data, if we it should be able to find a pattern and correlation with if you have the set of large data set, right? So that's one of the use case where I think AI and machine learning can help in to make easy the performance engineers job. So other thing is like automated performance stat analysis. So I talk about continuous performance testing, right? So it shouldn't be a burden to a QA engineer. And if the QA engineer has to come in the morning and every day morning and look into the performance stats and check whether response as time has gone up, whether latency, whether throughput, whether throughput has decreased, whether he has to do that manual analysis, then that guy will do it for only few days, right? So certainly, then it will be skipped after that, right? So if we can come up with the model, right? So there will be automated analysis going on with this continuous results coming in with the continuous testing, and if the alerts can be triggered in case of an anomaly and special situations, then the QA engineer can come in and look in. Then if we have that kind of model, then continuous performance testing will be success, right? So other point is like performance stat forecasting. So I'm not going to touch this much further because Malik is already covered this. So I think this also will be helpful in not in the developers concept, but it will help in us as well as performance engineers. So other point is like continuous monitoring and alerting. So I explained it a bit further on the continuous testing side of it. So other point is like observability, right? So so with the previous setup, I explained like we are collecting a lot of data. So if we can come up with a model where we can reactively make decisions based on this and trigger the alerts in case of anomalies and so on, right? So then there are certainly AI and ML can machine learning can help us, right, as a performance engineer. So these are the points where I see that AI and ML can help in to further improve the performance testing tools or the load generators, so that the QA engineers efforts on the life can be much easier. Because if we have to run the test repetitively, find the best capacity, and if we have to manually go through each and every matrices to figure it out the patterns and correlation, then it will be a lot of work, and we will be missing also some sort of a contest, right? So yeah, those are the main areas I want to cover within my session. I hope I am within the time as well. So I think we can take on questions if there are any. Paba, I think you can take over.
Okay, I hope everybody can hear me. So Malik and Asanka, we have a few questions. Let me start with the first question. Any one of you can pick it up and answer. So the first question is from Ramesh. And Ramesh wants to know, are there any insight on applying artificial intelligence in ops data and continuous tests, like using ops data by reading PRD logs, apply AI on same, and finalize user or transaction mix for tests?
Right. So ops data, I think he's referring to the operations data, right? So can you, I think you are going too fast. Can you repeat that question again? Yeah.
Any insight on applying artificial intelligence in ops data and continuous tests, like using ops data by reading PRD logs, apply AI on same, and finalize user or transaction mix for tests?
Right. So this is nothing is coming to my mind right now. So it's not an use case that actually we work on. Yeah.
Yeah,
Maybe
Malik, yeah, Malik, yeah, I think like ops data is a kind of a very broad term, right? So like if we get like a resource allocate, like resource utilization details, so what I was trying to explain, like if we get like, let's narrow down like from the performance testing tooling perspective. So if we have the matrices on JMeet or our load generator level resource utilization, right? So those details we can use to kind of better make decision in the next time, right? Or we have set up data gathered to those monitoring tools, and we should be able to and also we certainly we have to connect it with the load generator details like throughputs and thread counts, those load generator details as well, and maybe come up with a model, machine learning model, and then use it as a predictive engine for the future cases.
Yeah, so I mean, one possibility there is, I think I have seen this, people have even developed certain tools. I think Azure had this, where they collect the data and then they sort of give recommendations. So, when you deploy something, you will allocate certain amount of resources, right? But this is quite costly. So they monitor it, and then they say, basically, you may change your resource allocations to this for these new ones. So there are tools like that, but that is basically going sort of along the lines of cost optimization in this particular case.
All right. Let me go to the next question, Malik. This question is for you. It's actually two questions. The first part is, do you think we can use artificial intelligence to stimulate app and server behavior, that is latency, CPU, and memory utilization for different parameters?
Okay, so this is yes. Okay, so now it doesn't have to be artificial intelligence. So so to simulate, there is this concept called discrete event simulators. So you can, so this is actually almost relates to the last use case which I have described, right? So one way to basically understand the performance is to build a mathematical model, right? Which is the Kiving model which I have explained. You can also simulate a system, right? So basically there are simulators. You can Google for the term discrete event simulation. So discrete event simulation is actually it's not just for these servers. You can simulate a supermarket, for example, right? If you want to sort of find out how a supermarket works or kills, what is the optimal number of people, or you can have a checkout counter where you only allow 12 people in the queue, right? You don't allow it more. So actually in certain countries they have it, and then you can basically change that number, change the parameters. This is exactly what you're asking, and then see how it impacts the performance, right? So this is like a very interesting area, and people are using this extensively. So this is actually called operational research, right? So I guess, yeah. So it is possible. You can change the various parameters. You can change the throughput and latency, and then see what happens. And there's also two types of simulations you can do. One is the closed system simulations, right? So JMeter test is a closed system most of the time, right? You send the request and you get the response back. It's actually a closed system. But there's also an open system. You send a request and it doesn't come back, it just goes out. So these ones are actually called, like if you take a streaming use case, kind of, what's the term, fire and forget. So both of these type of systems you can actually simulate and understand, but what you have to understand is the latency and throughput are different. If it's a closed system, it's all controlled, right? Because you can't send the second sort of a response, second request until you receive the response. You send a request and then you have to wait till you get the response back to send the second one, right? Because it's a thread which controls it. So so the performance characteristics of these two types of systems are different. Yes, Papa.
All right. Thanks, Malik. The second part of the question from Hamza is, for example, when we test an app for 10 TPS and get the CPU and memory usage, using a model, what will be the CPU memory until if the load is twice or 3 times?
Yeah, can you repeat it?
Sure. For example, when we test and apply for 10 TPS and the CPU and memory usage, using a model, what will be the CPU and memory usage if the load is twice or 3 times?
Okay, so the initial one, did you say 100?
Initial one didn't have anything specified.
No, okay. One last time, can you repeat the question?
Sure thing. For example, when we test and apply for 10 TPS, get the CPU and memory usage, using a model, what will be the CPU and memory usage if the load is 2 times or 3 times?
Yeah, so you can't actually tell. It depends on what type of systems that you are going to test it. It is, of course, not linear, right? Now, when you increase the load, basically it depends where in the curve you are. So I have actually shown you some curves, right? So so when you increase the load, the TPS, the CPU utilization, all of these things are actually very much non-linear. So you can't really say this improves by this much.
Cool. All right. We have another question. Any initiatives from performance testing tools to use AI on their tools? Asanka or Malik, one of you can take it up.
Papa, can you kindly repeat it again?
Yes. Any initiatives from performance testing tools to use AI on their tools?
Not. I haven't seen actually on the public space, at least. So what I see is like if the base meter may be doing it inside, but they haven't exposed anything because they certainly should be able to do, because they are more of a cloud-driven platform, and so many people is using that, and with that they are actually gathering a lot of statistics and so on. So they have the data. I guess they should be able to. Maybe they're already using such a thing, but I don't see actually any public discourse about anything implemented. On testing tool perspectives, I don't see, at least on the tools I know, like for example, JMeter. If you take no direction, no, they are like JMeter. It's like I think it started on 1998. It's like very old stacks, and I think it's stuck there with the old architecture and also on. So maybe we can expect something like that kind of a thing from the cases kind of a model tool, but I haven't seen such a thing as of now.
All right. Thanks, Asanka. Last question for the day. How can we start to do some research and development for some specific problems, like predicting load generators?
Predicting load generators.
Yes.
Predicting load generator. I don't understand the question actually. What do you mean by predicting load generators? You mean, I think predicting the load, probably.
Yes, it says generators, but yeah.
Yeah, so the first thing is now you're asking a research, right? So you have to narrow down the problem. So that's the first thing, because these problems are like, at a very high level, quite broad, right? So you have to narrow it down and then understand what's the exact problem that you want to solve. And then basically then comes the data, right? Then you have to see what is the data that you have, right? So that would allow you to sort of do this, whatever, the load prediction or whatever, right? So depending on the data that you have, the complexity of the model that you build will vary, right? For example, if there's limited data, you will have to start with very basic models. So this is actually, we have seen this thing because initially, so when we are building the cloud platform, we have gone and, for certain use cases, very complicated methods like you may have said, I mean, not for exactly this use case, like GPT-2, GPT-3, we have tried those. But then what we realized was, so in the initial phases, if there's no data, there's no point going for these complicated models. So then what might work is actually very simple statistical and analytical models may work. So when doing these sort of things. Now these performance curves actually I showed you, we have in fact started off with using machine learning models. But what we realized was, so two problems. One is not enough data, because what happens is with machine learning, like machine learning models also have issues. Like, you may have heard like models like XGBoost, etc. They try to overfit, right? And then it completely get messed up. Like these curves, what we got was not acceptable at all. So this is lack of data and there is noise. Noise makes it even worse, right? So then you have to do the noise removal and then outlier removal and so on. Then after that, you sort of try to, build a model. And so when you don't have data, actually you can go with the completely analytical approach. Like, for example, just fit it to some curve which has a known form. So the solution that I showed you is completely actually analytical. I mean, it's still considered as AI because it comes under that category. When you have more data, then you can shift to machine learning side. Or there's a way to combine the two. You can combine analytical and machine learning models together. Analytical model will know the domain knowledge. It knows this behavior should be like this, right? So therefore, when you have little data, it will sort of force into that direction. So that's why the curves were actually kind of coming up quite nicely, right? But when you have more data, of course, then you can combine the two or completely go with advanced machine learning models.
Asanka, would you like to add to that?
Yeah, I think as Malis mentioned, like it's more of a data, right? How much data we have, we can go for better models, right? I think what we have what's the issue we have with the tooling stack as well, right? So it's hard to collect this kind of data unless you are like an enterprise and having a central platform as well ISP, right? So if we have like I guess mentioned like BlazeMeter has that, but other specific, like for example like JMeter is open source community and they are not actually running the test. So if we get K6, that's also open source and they are not running the test. Actually, organization using this. So the problem is like the tool is developed by some other guys and actually using by some other guys and data is with some other guys. So because of that, what I see is like the actually the applications side of it and on the application performance monitoring tools has moved with AI and machine learning. And for example, Dynatrace has their own capabilities, right? They can detect when once they install. We have to just install one agent on the machine. They pick up all the things. So they have moved on, but at least on the tooling side, performance engineering haven't moved forward. I think what I feel is like we are stuck in the 2000s still. So I think it's high time like new tools coming up and try to fill these gaps.
Yeah. So also another interesting use case, actually, what we are trying to work on, which relates to tooling. I'm getting some noise. Okay, now it's gone. Now one issue that we face, I'm not sure whether this is an issue for Asanka, is that when you try to run a performance test, you have so many parameters, right? Now we have different message sizes, the concurrencies, and so on. So, like for example, if you can't afford to run the test for like concurrency, so for each and every concurrency from 1 to 200, right? So what we usually do is you pick some and then you run, right? It's not possible to run the test for each of these combinations. So one problem that we are trying to solve, I think I'm exploring this as a research project. So there's an area of this area called design space exploration. Design space exploration. Basically, what it does is, when you have such large number of combinations of things, it kinds of, identify, go and run the test for these cases. And if you run it for these cases, then the results that you get would represent this system's performance accurately. So that's one thing that we are working on. I'm not sure whether it's relevant to Asanka, but yeah, it's a very interesting use case.
All right, then. It has been a really interesting conversation so far. I want to take this time to thank everybody here for being a part of PerfUp 2 AI in Performance Engineering. A special thanks to our speakers, Malik and Asanka. Really appreciate the time that you took on Thursday evening, just after a holiday, to spend time with us and really dig deep into this subject. Thank you to all the audience members for coming in, tuning in today. So see you at our next PerfUp session. We will be having our next PerfUp session in March. Stay in touch. And if you have any more questions to direct at the speakers, you can, of course, reach out to them on their LinkedIn, or you can even reach out to Cisco Labs social media pages, and we'll try our best to answer your questions. So again, thank you to the speakers, thank you to the organizing team for the PerfUp team, and have a good night and stay safe.
Thanks a lot. Thank you.